Okay, we have here a good one today. We've got the integral from 0 to infinity of e to the minus x squared cosine x dx. Now to get started with this, the first thing I notice is just e to the minus x squared. Now you may recognize this. This makes me think of the Gaussian integral. If we could just kind of get rid of this cosine x, right? The Gaussian integral is usually going from minus infinity to infinity. This is going to be half of it because we're going from 0 to infinity. This integral right here has a known value. We know this to be square root of pi over 2. But the question is, dealing with our problem here, is what are we going to do with this cosine x? This is kind of in the way. Now you may be familiar, sometimes you come across a kind of a different looking problem where we might have something, I guess this is like the most common example, something like this. Now in this case you can't really quite use the Gaussian integral over here, but the x is pretty easy to deal with because you can deal with this one with just a u substitution. Well, for this case with cosine x, it's not going to go away quite as easily as this case over here. We can't just do a simple u substitution to clean this up. But what we can do here is actually try to clean this up using Feynman's trick. Okay, so now for Feynman's trick, what I've done is I've created this parameter t on here. And so we have our f of t. This is going to be the same as our original integral as long as t is going to be 1. So we can kind of look at our goal, our original problem. What we want to find here is going to be just f of 1. And then the other thing we're going to want here is we're going to want some other value, not t equal 1, where we know how to evaluate this. Well, I think what's going to work is if t is equal to 0, you plug a 0 in here, cosine of 0 is just 1. So then what you have left is just going to be this part, which is the value we know for the Gaussian integral, right? So this value we know to be square root of pi over 2. So going ahead with this, what I want to do first is we just want to differentiate this with respect to t. And so what we want to do here is we want to bring this inside the integral and differentiate this as a partial with respect to t. And so when we do this, this piece right here with respect to t, this is actually just going to be a constant value for now. So we can kind of bring this up front here and put it right here. And then we just need to differentiate cosine tx. Derivative of that's going to be minus sine tx. But then we need chain rule differentiating tx with respect to t. That's just going to bring out an x. And then here you'll notice if we just group this x back with e minus x squared, this is actually what we saw at the beginning of the video. If we group these together, we can actually do this part with a u substitution. This part we can differentiate. So let's just use integration by parts on this. So I'll come over here and we'll do the DI method or tabular integration, just differentiating the sine tx. And then we're going to integrate this part, x e minus x squared. Derivative here, this is going to become minus cosine tx. Keep in mind we're differentiating with respect to x now. When you do that, chain rule of t is going to come out front. Now for this integral over here, let's just do this out really quick. We're going to have x e minus x squared. I just want to set up a u substitution for x squared so I can multiply in a 2, multiply by 1/2 in front. So we'll kind of do the u substitution in our head. Doing this, we're going to have 1/2 e minus u, which is going to be e minus x squared. But because we have the minus sign, we're going to bring a minus out front. And so our value for this is going to be minus 1/2 e minus x squared. So we'll have part of our solution on the diagonal. This last row is going to be an integral. So let me make a little space to fill in all these values. So for this diagonal, minus times minus is going to be plus. I can write this as sine tx over 2 e minus x squared. And we're evaluating this from 0 to infinity. And then here for all this stuff, minus times minus is plus, but we have another minus sign. I can bring t over 2 out front as a constant. So we're going to have t over 2, and then everything else is going to be just e minus x squared cosine tx. So then coming over first, evaluating this, you'll notice you plug infinity in here. The exponential is going to be much stronger than whatever sine's doing. So the first part when you plug in infinity is going to be going to 0. The second part, plug in 0, this e to the minus 0, this is going to be a 1. Sine to the 0 is 0, so this is all going to be 0 as well. So this whole part is going away. This is all going to be just 0. And then the thing to notice right here is this right here. This is identical to this part over here, and this is just f of t. So we can actually just simplify this down and call this f of t. And so what happens is we can boil this down to a very simple expression, just f prime t equals minus t over 2 f of t. And what we have over here is actually a differential equation. It's a pretty simple one. It's separable. It's pretty easy to do. I think what I'm going to do is, let's just kind of do this out really quick. I'm not going to get into too many details with the separable differential equation, but if I divide by f of t on both sides, we can write this as f prime t over f of t, and this is just going to be equal to minus t over 2. So normally if we were doing out the differential equation, we'd write this as like dy over dt and have dy over y. I'm just going to leave it this way to save a step. So what I can do then is we can differentiate on both sides with respect to t. On the left side, you could do a u substitution, u equals f of t, and you have your du right here in the numerator. What that means is this is actually going to become just natural log absolute value f of t. And sorry, we want to have an integral sign over here, of course. So we integrate this, we're going to have minus t squared over 4 plus c. So using log properties over here, what we can do is rewrite this absolute value f of t, and we can write this as equal to e minus t squared over 4 plus c. But then with the plus c and the exponent, that's going to be the same as e to the c, which is just another constant. So how I can write this is we can write this whole thing as c times e minus t squared over 4. I can actually drop the absolute value on this just because the absolute value is just going to be plus or minus 1. It's just going to be another constant, so it just gets absorbed in this constant. So we have this problem that we still have a constant we need to find, but otherwise we have our value for f of t. Keep in mind our goal is f of 1, so with f of t we're getting pretty close. Let me clean up the board and we'll just try to solve for this constant. Okay, so now we can deal with this constant over here. And that's actually why we created this initially. This is like our initial condition that's going to allow us to get that constant, hopefully. So what we can do is we can plug in, we're saying here t equals 0. So for our f of 0, we plug in, we have c, we plug 0 in the exponent, this is going to become just e to the 0. And we're saying this value is going to be square root of pi over 2. So we're saying c is just going to be this square root of pi over 2 value. So let's take this and put it back in for c here. Oh, that's terrible. So now plugging this back in here, we can rewrite our f of t function. So we have f of t is going to be square root of pi over 2 e minus t squared over 4. And now all we need to do for our solution is we just need to get back something for f of 1. So plugging in for f of 1, we're going to have square root of pi over 2. Plugging in 1 here, we're going to have e minus 1 over 4. And that's it. I was trying to look for a better way to write this. Like I could bring it all into all under a square root. So if we wrote this, we have it as square root of pi over 4 square root of e. I could write it that way. I guess one more way we could write it as, I could write this whole thing as a 4th root. So we'd have the 4th root of pi squared over 16 times e. So I don't know which way is the best way, number 1, number 2, or number 3. I don't know. Anyway, there you have it. Good problem today. Thanks everyone for watching. Have a good day.